So, get your thinking cap on and get your pen out. Here's where we're going to start, okay? You can make a little subheading. This is a proof, okay? Now I'm going to give the proof to you two ways. It's a proof that, unlike most proofs, you are expected to actually be able to replicate. I'm going to give it to you two ways. It's a proof of acceleration, x double dot, in terms of displacement, and also velocity as well. We'll talk about that in a second. I'm going to give it to you backwards first, because I actually think the backwards way it makes more sense. And then second, I'm going to give it to you forwards, the way that you would actually produce it if the question was, prove that, and I'm going to give you the result in a second. Okay? So, here's where we're going to begin. I'm going to start at the end. Okay? So I'm going to say, acceleration. Okay? What is acceleration? Acceleration, we said before, we already know what it is in terms of time, as a function of time. So it's about how velocity is changing over time. Yes? But I said just now, I want to try and take this kind of equation and sort of translate it, if you like, so that it's not a function of time but of displacement. So I've got, I just rubbed it off. So I've got dx's flying around rather than dt's. Okay? So what am I going to do? You remember with chain rule, right? We're used to thinking of chain rule as this. You've got y, you've got x, and you introduce some new function, right? Like so. Okay, but the key idea was that these du things, right? You can shift them around and cancel them, and they're interchangeable, and that's what makes chain rule work. Okay, so I'm going to do something similar here. Now remember, I wanted things in terms of x's, so I'm going to multiply by dx on dx. Come in.
Do you have an neck on that?
Yeah, I do. Catch. Sorry. Okay. Is it that cold? Or hot?
It's cold.
Is it? Do you want to shut the... Anyway, okay. You can shut the windows. Alright, where was I? What have I done here? Answer, not very much. Okay, and it's important that I haven't done very much. There's no net change, just like with chain rule. Okay, I mean, you can write this as dy and dx times du on du. Right? It works because I haven't actually changed anything. But now let's rearrange this so it's actually something a little more useful to us. Okay? I'm going to swap around some of the denominators and numerators. Okay? So let's put this dx over here. I'm going to get dv on dx. Okay? So I'm switching around the dt and the dx on the denominator. Okay, now, what does this look like? Is this any improvement? It is a little bit, okay, because my aim is to get rid of the t's, right, so that they're no longer in terms of time, but they're in terms of displacement, okay? So you can see here, that derivative is something I know, right? I recognize that, and I can get rid of the dt's because this is velocity. You see that? dx on dt. How x is changing over time. Okay? So I'm going to write this as v dv on dx. Okay, come in. Thanks. All right, now, so far so good. This is actually a helpful point. I'm going to come back to this line in a second because in a sense I have gotten rid of my t's, but I can go a little further, right? This guy here, I want to get it so that I don't have this bit here. I want something else, more in terms of the actual original function. Okay, so I'm actually going to do a weird step in here, which is say that v, if I integrate that, right, with respect to v, integral of v with respect to v. Okay, what is that? Good. Plus your constant, of course, right? Now, why is this useful? You'll see in a second why, but it's a bit of a strange sort of why would I do this, okay? Taking this, that means that v is, I'm going to differentiate both sides now, okay? So if I differentiate this side, I go back to what I was integrating. And if I differentiate this side, I'm going to get d on dv of half v squared plus a constant, okay? And don't forget, when I differentiate, that constant's going to vanish. Okay, so that's actually the derivative of half v squared. Okay, so I'm going to take this result, which is v. Okay, and I'm going to pop it in here and see what happens. So I've got the derivative, of half v squared. And I've got this other derivative hanging off on the side. Okay, now, why was this useful? Why was this useful? Why is this a better step than the previous one? Because, just like in this line, right, what I've got is these two differential operators, right, that here I can cancel, right? These two dv's, they're going to disappear because of chain rule, okay? So this dv and this dv are going to be no net change, okay, so I'm going to get rid of it. But I can't just be d of whatever, okay? I want to be d on something else. And what's left is my x, right? So this cancels, I'm left with d on dx of half v squared. Okay? That is x double dot, or acceleration. Okay? Now this is the result. This is acceleration or force in terms of displacement, right? Also velocity is sort of in there as well, but we'll usually get velocity as a function of x, as I'll give you an example in a second. So this is kind of cool, right? Function of displacement. So we're getting towards this kind of understanding. These kinds of scenarios where your motion is governed by how far apart things are rather than when the time of the scenario is. Okay? But also, I'm going to draw attention to this part here. This is acceleration as a function of velocity. Okay, now that's kind of useful as well. We're not going to dwell on this, but it's kind of an interesting result that in the physical world you've got objects that behave like this when they're moving. For instance, when you throw something through the air, okay, we've sort of been ignoring this, right? But if you're going fast enough, your object, right, it gets slowed down by the medium that you're traveling through, right? Like air or water or those kinds of things, right? So in other words, your acceleration changes as your velocity changes. Okay, the faster you go, the more different forces like air resistance are acting upon you. Okay, so you can get acceleration in terms of velocity, how fast you're going, or in terms of where you are. Okay.